All right, we are going to be talking about energy flow today. So you have your essential question. How do we describe the movement of energy into or out of a chemical system? So there's going to be a lot of vocabulary involved in this particular unit, so we want to make sure and pay attention to the language of the notes. So we're going to talk about the first law of thermodynamics, also known as the law of conservation of energy. And basically what that means is that the energy of the universe is constant. All of the energy that's here has been here since the beginning of time. Now, that doesn't mean that it's static or not moving. We are constantly, energy is being absorbed, energy is being released, it's being transferred, right? But we don't create it, we harvest it. All right, energy can be converted from one form to another, but again, it cannot be destroyed. And down here is an example of energy transfer that you've probably seen happen before. So if we take this ball, we're on a hill, and this person, now right now, this ball has what we call potential energy, and that's the energy, stored energy. So it's stored within the ball, and being on this hill, this person is going to let go of that ball is going to start rolling, and that potential energy is going to get converted into kinetic energy, and it's going to then roll down the hill. Now, I'm sure you all know what's going to happen to this ball when it hits ball B. Ball A hits ball B. We're gonna hear a sound. We might hear a crack. You might see a vibration, but definitely energy is going to be transferred in the form of sound, vibration, and absorbed energy to the ball, because then all of a sudden that ball is going to clack, and we're going to see, again here, and the ball is going to have enough energy to start it moving until it will come to a rest. All right, so again, this is just supporting the idea that energy is transferred between objects. A second way that we look at it is in the energy in a chemical reaction. So we study chemical reactions, so we know we can take gasoline and oxygen, and when we do, it's a hydrocarbon plus oxygen. It's a combustion reaction. We're going to get two products. We're going to CO2 and H2O. We know that one of the ways that we can identify this reaction is because of the heat and light that's given off in that explosion. So again, that it is a transfer of energy that comes from the reactants, gasoline reacting with that oxygen. Down here at the bottom, we can look at those energy changes in a graphic form. So this is a terrific graph that we're going to be actually talking a lot about in this particular set of notes. So let's just go ahead and go on. Again, this idea though that nothing disappears. So law of conservation of mass says that all of our matter is conserved. Like, it's not magic. We're not going to produce something out of nothing. And then we have the first law of thermodynamics, which is that the energy that is generated in this reaction comes from within the chemicals that have reacted. And that's also conserved. All right, chemical systems. So the universe can be divided into two ways. So how do we talk about energy change? We want to talk about it, and we have to kind of narrow it down, right? We want to talk about the system and everything else around it. So the system is the reaction that you're looking at. The surroundings obviously is everything else. So as we look here, this little gray box, this is our system. Maybe it's a beaker, right? Maybe, it's a beaker that I'm putting things together, I'm combining them together, and a reaction takes place. So the surroundings is everything outside of that beaker. All right. Now, in this particular situation, what happens when the system, as a result of its chemical reaction, is releasing heat? So heat is going this way. We would say heat is being given off to the surroundings. By the way, pay attention in these notes. Anytime you see a draw this, you want to make sure and do that in your notes. In this one, we have our system and our surroundings. And in this case, the energy is being absorbed by the system. All right, so it's taking the energy away from the surroundings. All right, this is giving energy off to the surroundings. So this might be that combustion reaction that we just saw, where that heat and light is produced. If you were standing there, you would feel that heat. That heat is being given off by that reaction. Here, this might be you've had an injury on a sports field, and you get one of those cold packs, and someone breaks it and they put it on your knee. And so what happens inside of that cold pack is a chemical reaction is taking place. And it's a chemical reaction that is absorbing energy from the surroundings. So when we put it on your skin, you're a part of the surroundings. It's absorbing energy from your body and you feel cold, okay? All right, and we have two language terms. We have endothermic and we have exothermic. So these are great terms. First of all, therm. Think about that word therm. So a thermometer, a thermos, exothermic, right? So the therm, essentially you can think of as heat, right? So a thermometer is a device that measures heat, right? A thermos is something that we put fluids in to either keep them hot or cold, depending on the situation. And then we have prefixes, exo and endo. So exo means outside and endo means within or to be taken in. So outside heat, heat given off. Inside heat, heat absorbed. All right, so just a little vocabulary there. We have to use the language of the course. So when we're talking about what happens to the heat, we don't necessarily want to say, well, heat is given off. Instead, we're going to say, oh, well, this is an exothermic reaction. If heat is being absorbed by the system, we're not going to say, well, heat's being absorbed or it's taken in. We want to use the language of the course and say that would be an endothermic reaction. Here are some examples of endothermic. Now, first of all, I do want you to draw this graph. So go ahead and stop. All right, welcome back. Let's just talk about what you just drew. We have a graph, and here is the potential energy. So we can see the potential energy is increasing as we go up, and here we have time. We have starting with our reactants. So here we are, time 0, before anything has happened. Here's our reactants, right? And sometime later over here is our products. And I hope that you can see that right now the energy of the products is lower than the energy of the reactants. That's really important. Now here we have something called delta H. Delta means change. H is an abbreviation for something called enthalpy. And again, that's not necessarily important for you to know, in that I'm not going to test you on it. I'm just letting you know that it is a very specific thing, and it is, enthalpy in general is just looking at how energy changes in reactions. So a change in heat, all right? So we can say the energy of the products, I'm going to say energy of the products is greater than the energy of the reactants. No, not greater, less. Less than the energy, I hope I said that right now, I might have said it wrong, energy of the reactants. All right, let's just make sure I didn't mess this up. I hope that you can see that the energy of the products is less than the energy of the reactants, if I said that right, absolutely right. And what this really means is that energy is released in this reaction. So we're going to take a look at some examples of exothermic processes. Their potential energy diagram would be similar to this, in that every one of them, the energy of the products is going to be lower than the energy of the reactants because they are releasing heat. Pause. Oh. I don't know what I did. first one, again, combustion reactions, we've studied them. They give off heat and light, definitely exothermic. Oxidative respiration, if you've ever been on any kind of sports team, you understand that when you exercise, your body starts releasing heat, right? You are giving off energy. That is an exothermic process. Freezing water. Now this is a good one because a lot of times students have trouble with this. Like, freezing water gives off heat? Absolutely. I mean, you think about it, take a glass of water. If you want to freeze that water, what do you do with it? You put it into a cold box. And within that cold box is taking heat away from the water until it freezes. Here's another little fun example. I love this one. We have a supersaturated solution. We're going to put a little ice cube in there, and instantly it freezes. Chemistry is so cool. All right, condensing. Water vapor. Okay, condensation. So there's water vapor in the room right now. If you've ever held your hand over a pot of boiling water, which we all do, like, how long can I hold my hand there? Maybe I'm the only crazy person in the world, but these are the games that we play. And you will feel that water vapor is coming up and it hits your hand and it starts to condense on your hand. Now, when it condenses on your hand, condensation is going to release heat. So if it's condensing on your hand, that heat is being released into your hand and you're going to go, ow, that's burning. All right, now we're going to look at examples of endothermic processes. And we're going to start here. So take a minute, stop the video, copy the graph. Welcome back. All right, so again, let's take a look at this. In this situation, same graph, we have potential energy, we have time. We can see here, here's where we're starting. These are our reactants. So what can we say? We can say here, the energy of our reactants is less than the energy of our products. So when that happens, when our reactants are lower in energy than our products, we are going to call this an endothermic reaction, all right? Heat is absorbed here, not released. And we know that because the products are higher in energy than our reactants. Okay, now let's take a look at some examples of endothermic processes or processes. Whoops, oh, I like that one, let me go back. All right, this is a fun little reaction. We're still working on making this happen as a demonstration. If you happen to be in chemistry again next year, you might be able to see this one live here at Garden Grove High School. We take a chemical, we're gonna mix it up, and what happens is we put a little water on a board. This is so endothermic that it absorbs heat, and as soon as you put it on that water, it freezes that water. And so it looks like a little magic trick in which the glass suddenly is now lifting with it, underneath it, a board. All right, so what's happening is there's water on that board, and this is so cold, it's absorbing the heat out of the water, causing for it to freeze. Isn't that exciting? Photosynthesis is an endothermic process. If you were all sitting here with me today, if I asked you, what's gonna happen if the sun doesn't shine? All of you would tell me, the plants are gonna die, right? The reason that is, right, the plants have to absorb the sun's energy. That means photosynthesis is an endothermic process. And by the way, did you notice that photosynthesis, endothermic, respiration, exothermic? Melting of ice. Most of you would understand that, yes, if I take an ice cube out of the refrigerator, it is absorbing heat from the surroundings. That is endothermic. And boiling water. And a lot of times, this one's a little bit tough for students. They think about the fact that when water's boiling, it's giving off heat. Yes, but how did it get that way, right? What does it take in order for us to get water to boiling? And that means that water, liquid water, has to absorb energy, which is an endothermic process, in order to boil. Why are some processes endothermic while others are exothermic? Chemical reactions happen in two ways. So again, here's another really important thing for you to know. We've already started talking about bonding, right? We have ionic bonds, we have covalent bonds, we've got metallic bonds, and we know that bonds are formed and bonds are broken. And I believe we've already talked about the fact that breaking bonds always requires energy, which means that bonding, in order for bonds to form, is an endothermic process, right? Has to absorb energy. No, I'm sorry, I said that wrong. Breaking bonds, you have to absorb energy, right? Breaking bonds absorbs energy. When I form those chemical bonds, so when new bonds will form, that is an exothermic process, all right? So breaking bonds releases energy, absorbs energy, endothermic. Making bonds releases energy, or exothermic. And what determines whether a substance is going to be endothermic or exothermic is the balance between those two processes. All right, so you can take a look down here. If the amount of energy that is required to break the bonds is small, and the amount of energy to make the bonds is large, or larger than this, right? This is small, this is big, then the overall reaction is going to be exothermic. If we look here, if the amount of energy to break the bonds, and breaking bonds, endothermic, right? This is endothermic, and the amount of energy released in the formation of those bonds, the exothermic, then this overall process, because this is big and this is small, then the overall process is endothermic. All right. So again, this basically says the same thing, that again, more energy is used in breaking those bonds than is released in the creation of the new bonds. And that's for endothermic. And for exothermic, more energy, we use less. So in this one, there is less energy used to break the bonds and more energy produced in the creation of new bonds, making this an exothermic process. All right, so how does heat flow? What I found historically is students pretty much kind of understand that heat flows in one direction, from hot to cold. All right, so heat is the flow of energy due to a temperature difference. Okay, so again, here's the hot, and what happens to it? Well, everything that's next to it, the heat will flow from a hot object to a cold object. Now, this also means we have another law. It's the second law of thermodynamics, and it says that the entropy of the universe is increasing. That means the energy of the universe is always going to disorder. Result when things, including energy, become more disordered, they tend to spread out. So again, it's just the idea that heat flows. This is why heat energy spreads out. Heat flow stops if there's no temperature difference in between the two objects. So great graphic here. Again, take a look. Here is our hot, and this side is cold. And we assume we have a permeable membrane here, or they're in contact with each other in some way. And the heat is going to flow from the hot to the cold until the two sides reach what we call thermal equilibrium, because now they're both the same temperature. So no net energy flow because there's once they get to the same temperature, then there's not really any temperature change happening between the two objects. So thermal equilibrium is when the two objects are at the same temperature and there's no net heat transfer between them. All right, let's come back up here. Heat always flows hot to cold, right? When is heat going to stop flowing? When the two objects become the same temperature. And when they become the same temperature, we're going to call that a thermal equilibrium. Going the wrong way. Nope. All right, how heat flow spreads out. Okay, conduction. Oh, this is conduction, convection, and radiation. Okay, so conduction. Contact. Transfer of heat to another object or substance with which it is in contact. So this is when we're cooking with a pan, right? When we're cooking with a pan, that heat under that pan, the sides of the pan are not touching the heat necessarily, but all of us know that as you heat that pan up, that contact that happens, the conduction occurs within the metal and the entire pan will heat up. Convection is when a warm substance rises above its cooler surroundings. So again, this is, heat rises, cold falls, right? The reason that your heater vents in a car are at your feet, right? Because heat will rise, and your air conditioning is up higher towards your head because cold will sink. Radiation, we have studied electromagnetic radiation, and again, the idea that light gives off heat. All right, so when electromagnetic waves carry energy from an energy source. So we have a wonderful fire here. And in this fire, if you'll notice, and I know it might be hard for you to see through this video, but you definitely can see it through the PowerPoint. And if there's not, this would be a great thing for you to draw. But here's this fire. And as you're standing next to it and you put your little hands there, you go, oh, this feels so nice. What are you really experiencing? Well, you're experiencing radiation. You can also be experiencing some of the convection because, again, the warm is rising off that surface. And if you are holding on to something like, let's say you're roasting a marshmallow, you might even experience that particular metal, if you're using metal, getting hot via conduction. All right, consider this. What does hot and cold mean? I love these. They're so cute. Okay, hot is what you feel when energy flows into you. So when you touch that burner in your kitchen, which, by the way, disclaimer, do not touch a burner in the kitchen. Okay, that's not a good way to figure this out. But if you did ever do it when you were a child, and many of us have made those mistakes, instantly you touch it and you go, oh, it's so hot. Well, what is hot? Hot is the fact that your hand, right, you as a live organism are giving off heat, right? But when you touch an object that is hotter than you, the heat always flows from hot to cold. You are the colder object. So that heat then is being transferred from that object to your hand. And if it's significant enough, your instinct is going to be to pull your hand away and go, wow, that's hot. All right? Cold. Cold is when your heat, give it off, right? And you touch something and heat is not being given off by the object. Instead, the object is absorbing heat from you. And if you've ever tried to hold an ice cube in your hand, how long can I hold it? You know that as that ice cube starts to melt in your hand, where's it getting the heat? Well, sure, it's getting it from the surroundings, but you're a part of the surroundings, so it's also taking heat away from you. So cold is when you feel cold, right? What does hot and cold mean? So if I say something is cold, it's because it is taking heat away from me. If I say something is hot, it's because it's supplying heat to me. Stick your hand into ice cold water. Fun little game, right? Energy is flowing out of this poor child into the ice cubes because the ice cubes are melting. If you take your hand out and you instantly go put them under even cold water, the cold water might actually feel warm because the water is at a higher temperature than your skin is. So hot and cold is relative. It's all a matter of perception. And again, hot packs and cold packs. So you probably are familiar with a cold pack, if you're an athlete at all, you break that, a chemical reaction takes place that is absorbing energy. You put it on your hurt area to help reduce inflammation after an injury, and it's going to take heat from your body, which is going to make the area cold. If you've ever gone to the mountains on a very cold day, you might put a hot pack in your pockets or in your shoes even to keep your feet warm. And same idea, we take two chemicals in that pack, we break something and cause for those two things to react together. They're going to give off heat, and you're going to have your hands on a really cold day, and your fingers and your toes are nice and warm in that extremely cold temperature. All right, that's it.